It's a great pleasure, of course, to be here in such a friendly atmosphere to celebrate the birthday and the mathematics of Alex Descartes. I'm going to talk about algebraic approximation of submanifolds of real algebraic varieties. And let me first explain the context of these kind of questions. So if you take over the reals a smooth projective algebraic variety, you can consider its set of real points, so the set of real solutions of the equations defining x, and it is a compact C-infinity manifold. And a kind of converse to this construction was given by the celebrated theorem of Nash and Tognoli. Which says that any compact C-infinity manifold is diffeomorphic to such a set of real points. So to x of R for such a x. And there are many extensions, variants of this theorem. That have been obtained, say, in the 80s. And for instance, the following theorem that you can find in papers by Agbulut and King, and also in papers of Benedetti and Tognoli. Where instead of looking at one manifold, you look at a pair of manifolds. So any pair, n inside of M of compact C-infinity manifolds, is diffeomorphic well to a pair of real loci y of R inside of x of R, where y and x are smooth projective varieties over R. And the kind of question I want to consider today is really this exact question where we, instead of being able to choose arbitrary algebraic structures y and x on n and m, where I fix the algebraic structure of the ambient variety m. So what if the algebraic structure of M is fixed? So I'll be more precise. So in all this talk, I will fix the following notation. So I fix the ambient variety. So it is a smooth projective variety of some dimension n. And I also fix a compact submanifold of its real locus. And the dimension of the submanifold I will call D. And the codimension of the submanifold I will call C. So really n is C plus D. And in addition, the inclusion of the submanifold inside the real locus, I will denote by I. Just the inclusion map. And of course, now it would be stupid to ask if n is the real locus of an algebraic subvariety of X, because n is a compact C-infinity submanifold. It's defined by C-infinity equations inside the real locus of X. It has no reason to be defined by algebraic equations. So this would be a naive and stupid question. A better question would be, okay, maybe n is not defined by algebraic equations inside the real locus of X, but maybe if I perturb n a little bit, I move it just a little bit, maybe it becomes algebraic. And so the question is, can one approximate n inside the real locus of R by an algebraic submanifold? So I will make it precise in 1 second, but let me first draw just a picture. So typically, this would be the real locus of X. Then inside it, we have the submanifold n, defined by C-infinity equations. And we're looking for a real algebraic subvariety here that is very close to the given submanifold. So this is what we are looking for. Okay. So I think this picture should make clear what I mean, but I'm still going to give a precise definition of what we are going to consider. So what I call property A, and A is for approximation. Okay, it is the property that for all neighborhood, okay, U inside of the space of C-infinity maps from n to the real locus of X. So neighborhood of what map? Neighborhood of the inclusion map. One can find a map, let me call it J, in this neighborhood, and a real subvariety Y inside of X that is smooth along its real locus. Such that the image of J is the real locus of Y. So what I mean here in a precise way is that if you perturb just a little bit the inclusion in the C-infinity topology, you get the real locus of a real algebraic subvariety. Okay. And the hypothesis here that Y is smooth along its real locus, it's really the natural hypothesis in real algebraic geometry. So smooth along Y of R is really what in the book by Bornach, Coste, and Roy is called a non-singular real algebraic subvariety. So that's the approximation property that has been classically considered in real algebraic geometry. And so this is the property I want to study. I want to understand when this property is true. Okay. So not always. There are obstructions. To the validity of this approximation property. And the finest obstructions are based on Bordism. And so I'm just going to define what I need.
But I mean, also like complex stories which have no subvarieties, right?
I'm looking for algebraic varieties, projective ones. I'm only looking at projective varieties. So I will define MOD of the real locus of X. So this is the dimension D Bordism group. It is really generated by C infinity maps from a compact C infinity manifold of dimension D to the real locus of X up to some equivalence relation, which is the cobordism equivalence relation. So where two such maps, F and F prime, are cobordant if, well, let me draw a picture. So here you have the real locus of X. Let me take the first map F from M to the real locus of X. Then I have a second map F prime from M prime to the real locus of X. And the cobordism relation between these two maps is, well, that there exists a smooth manifold with boundary here and a map capital F that extends F and F prime. Okay. Now, inside this, this Bordism group, one can consider the subgroup of algebraic Bordism classes. So inside this group, I consider the subgroup generated by all smooth maps, all C infinity maps of the form, so by the maps induced by algebraic morphisms between smooth projective varieties. And my point is that if you want to prove that the inclusion of n in X of R is approximable by algebraic maps, it better be cobordant to algebraic maps. So,
Why is it the finest?
Sorry?
Why is it the finest?
I mean the, okay.
Say, for example, homotopy would be probably more restrictive.
Sorry?
Homotopy would be more restrictive, I think. More difficult to come.
No, because if two maps are homotopic, then they are cobordant.
Yes.
Because the
That's what I mean. So homotopy would be more restrictive than the body. More difficult to compute, of course.
I mean,
It could be cobordant algebraic, but not homotopic algebraic, right?
it could be cobordant to an but not absolutely, yes.
Yeah.
It could, yes, yes.
I just object your statement that this is the finest.
I don't mean strictly finest, but it. Yeah, yes, I think, I don't know. Okay, the reason why I wanted to write finest really is that more classically, obstructions using homology have been used. And this is really finer than the classical obstruction using homology. This is really what I meant by finest. I won't debate if it's really the finest you can write down. And really, I should quote Borchnack and Courage for using obstructions based on cobordism, to obstruct approximation.
Let's agree on a finer.
Okay. Okay, let me write a fine one is best. Thank you very much. Okay. And my point is that now you can use bordism to write an obstruction to approximation. What I mean is that my approximation property implies a property I'm going to call property B. And B here is for bordism. And the property B is the assertion that the class of the inclusion of n inside the real locus of X, which I view as a class in the bordism group of the real locus of X, is an algebraic class. In other words, it's the assertion that the inclusion is cobordant to an algebraic morphism. And let me state again that, okay, Borchnack and Courage were the first to use this to obstruct approximation problems. Okay, let me make a couple of remarks on this property. So the first remark is that, well, if you don't like bordism, then in fact you can reformulate this property using only homology. And more precisely, property B is equivalent to the assertion that, so when you take a product of Stiefel-Whitney classes of n, so those are Stiefel-Whitney classes, they live in the cohomology of n with mod 2 coefficients. And when you push forward this product by the inclusion, then you get a cohomology class of the real locus of X with z mod 2 coefficients. And B is equivalent to the fact that all these classes are algebraic classes. So it contains the information that all push forwards of products of Stiefel-Whitney classes are algebraic cohomology classes. Okay. So of course you see now that this is not a purely topological property because it's very much influenced by algebraic cycles on X, by what, not only by the cohomology, but also inside the cohomology by the algebraic part of the cohomology. And as a consequence of this reformulation, you see that property B is always satisfied on a variety whose cohomology is totally algebraic. And so, for instance, on projective spaces, Grassmannians, products thereof. On projective spaces, Grassmannians, products. And on your favorite varieties with totally algebraic homology. Okay. So I have stated an approximation property, and I have given a necessary condition for it. And of course, now I want to ask, is this necessary condition also sufficient? And my first theorem is a result in this direction. It says that if the dimension of the submanifold is strictly smaller than the codimension of the submanifold, in other words, if the dimension of the manifold is less than half the ambient dimension, then the two properties A and B are equivalent. Okay, in particular, since B is always satisfied on Grassmannians and so on, in this range of dimension, property A is also always satisfied on such varieties. Okay, let me make a couple of remarks. So, of course, okay, if D is equal to 0, we are considering points, and of course, points are algebraic, and the result is obvious. Already for curves, the result is not obvious. So it was proved by Agbulut and King under a technical hypothesis, which was removed by Borchnack and Courage when the ambient variety has dimension 3, and by Olivier Wittenberg and myself in general. And okay, and if you look at subvarieties of dimension 2 or more, I think the result is new.
So for curves in surfaces, this is not true.
It is true, absolutely. In fact, curves on surfaces are divisors, hypersurfaces, and hypersurfaces are very particular. Approximation is much. Yeah. The case of divisor is very particular.
I didn't understand what you say, that in this range B holds.
If A holds, A and B are equivalent. So on projective spaces, B holds. Yeah. Okay, so now, of course, I have an hypothesis on the dimension of D compared to the dimension of the ambient variety. And it's a natural question if it is necessary, if I can remove it. And the second theorem tells you that I cannot completely remove this hypothesis. So if D is greater or equal to C, and C is not arbitrary, as a special shape, is of the form 2 to the k plus 2 to the L minus 1, where k and L are distinct integers, then one can find x and n as above, for which the Bordism property holds, but the approximation property fails. So really this hypothesis here is sharp for infinitely many values of the codimension. Okay. Again, I should make a couple of remarks. So the first remark is that to the best of my knowledge, those are the first examples showing that A and B are not equivalent. So the second remark is that, well, theorem 2 gives examples for many values of C, so 2, 4, 5, 8, 9, etc. So from infinitely many values of C, but not for all values of C. As I explained 1 second ago, there cannot be such examples for C equals 1 for divisors. So no such examples. For C equals 1, just because it is not difficult to approximate C infinity hypersurfaces using the fact, the relation between hypersurfaces and line bundles. It's well explained in the book by Borchnack, Coste, and Roy. But for C equals 3 or 6, 7, I do not know. So I know absolutely no counterexamples for C equals 3. C is what? No, because K may be equal to 0. So yeah. So 0 and 1 are going to give 2. Another remark is that Courage and Van Hamel have asked if the approximation property always holds when the ambient variety is projective space. And I do not know the answer to this question. I cannot build counterexamples when the ambient variety is projective space, which is the most interesting ambient variety, of course. Okay, and the last remark is that the simplest example I can construct which is for surfaces in a fourfold, so C is equal to D is equal to 2 and N is equal to 4, is the following. So the ambient variety X, it's a product of projective spaces. It's P1 times P3. The submanifold, well, it's the surface P2 of R. And the embedding, well, you embed P2 of R in the way you want inside R4. And then you view R4 as an affine chart in P1 of R times P3 of R, which is the real locus of X. And I claim that the approximation property doesn't hold for such choices. It's not possible to find a real subvariety of P1 times P3, smooth along its real locus, with real locus very close to a P2 of R, embedded in R4. Are there questions? Why what?
Why does this hold?
Okay, so I'm going to say something, and maybe I'm going to answer your question in 2 minutes, if you. But I need something to erase. Here it is. So the next thing I want to explain is the reason why this hypothesis about D and C appears, or why this threshold between D smaller than C or D greater or equal to C. So the D smaller than C hypothesis. So I'm going to explain it informally. It's a Whitney type hypothesis. And what do I mean by that? I'm referring to Whitney's theorem that any d-dimensional manifold can be embedded in R2D plus 1, so Whitney's easy theorem. And why does it matter here? my point is that imagine you have your ambient variety X, and you want to construct a smooth subvariety of X, which here is going to have real locus approximating n. If you construct a subvariety y of X, this has dimension c plus d, this has dimension d. Just by generic projection somehow, where W here is smooth of dimension d. Well, if the projection is somehow generic, if this map is generic inside the space of C infinity maps, you expect this map to be an embedding under this hypothesis. And so you expect Y to be smooth only under this hypothesis. And if D is smaller than C, Y is expected to be smooth. Okay, if F is generic enough in the space of C infinity maps, and if D is equal to C, then typically W is expected to self-intersect in X, and Y is expected to have a finite number of double points. W is expected to self-intersect in X, and Y will have finitely many double points. So self-intersections. So this is the heuristic to have in mind, and let me tell you one word about how this heuristic enters the proofs of Theorem 1 and Theorem 2. So in Theorem 1, well, the subvariety Y is really constructed in this way by a generic projection somehow. And so the hypothesis D smaller than C is going to be used to show that it is non-singular. So Y is constructed by such a generic projection argument. And okay, so this hypothesis is going to ensure smoothness of Y, at least along its real locus. Okay, and in Theorem 2, the argument is inspired by this remark. The idea is that, well, imagine, okay, you have this subvariety Y of X, whose real locus approximates N, and imagine it comes from some generic projection. Then it's going to self-intersect in a certain number of double points. And I'm going to count these double points. And I will count them, and I will find that there is I will count them using a double point formula, and I will show that this number of double points is non-zero. And in fact, that it is odd, and so one of them is going to be real. And
but I mean, Theorem 2, the idea is clear, but for Theorem 1, how can you do generic projection if you are not in projective?
yeah, this is the reason why I still have 25 minutes in my talk. This is the so count the number of double points using Fulton's double point formula. And deduce that this number is odd. And hence there is a real singular point. There is. One of them is fixed by a complex conjugation, and there is a real singular point. And of course, it is a computation that you need to make. It's not non-trivial. I'm not going to make it. What is surprising is that you have enough information just knowing the real locus of y, that it's very close to n, to carry out this computation. You only knowing what the real locus looks like is sufficient to make this computation. And maybe I should, since I will not talk about theorem 2 in the rest of the talk, maybe I should say that the main tool are congruence results for Chern numbers. And I rely on work by Rees and Thomas. Are there questions? So if not, in the remainder of the talk, I want to explain how theorem 1 is proved in more detail. So recall the setting. So we have X over R, smooth, projective, of dimension C plus D. And we have N inside the real locus, a compact C infinity submanifold of dimension D with D smaller than the codimension. So strictly smaller than half the ambient dimension. And I. So I have the assumption that I is cobordant. This is my Bordism hypothesis. To an algebraic morphism. And in this situation, it is a theorem to, okay, so by a theorem due to Agbulut and King, and also to Benedetti and Tognoli. The inclusion may be approximated by an algebraic morphism. So the hypothesis is that I is cobordant to an algebraic morphism. It may be approximated by algebraic morphism. So, and this statement really is a relative, if you want, version of the Nash-Tognoli theorem. So let me tell you what it means and why it doesn't solve the question immediately. What you get is a morphism from W to X of smooth projective varieties over R. Such that at the level of real points, it's very close to the inclusion.
About this group, so you might need two smooth varieties, and then the sum of these maps is.
Yes. Yes, maybe. And yeah, maybe. But I didn't ask my varieties to be connected.
In what sense it's close to I?
So in the infinity topology.
No, but I mean they have, a priori they have different...
So, okay, you can identify, you can find a diffeomorphism between the real locus of W and N.
So W is related to N.
Exactly.
Yeah.
Okay. So, yeah, absolutely. In this sense, there is a diffeomorphism here. Thank you. And why doesn't it solve the problem? Well, the problem is that this map will typically be not injective, and it may have positive dimensional fibers even. And so it's very possible that there are two complex conjugate points of W that are sent to the same point in X. And then this will give rise to a real singular point of the image. Those are the self-intersections I was talking about. So the difficulty here, F may not be injective. So two complex conjugate points of W may have the same image by F. And that would give rise to a singular real point of the image of W by F. And so the image of W by F doesn't solve my question. It may have a singular real locus.
So this is anything it falls for any dimension to them.
Absolutely, absolutely. It's a very general theorem. Yeah, and absolutely. And in the rest of the proof, you want to use this hypothesis to modify F so that this difficulty does not appear anymore. So now what do I do? I'm going to work in some ambient space. I will embed W inside a relative projective space over X. So I embed it in P big N times X. And I will call pi this projection. And now the idea is to move, in some sense, W inside this space. To get another subvariety of this space. which satisfies the following properties. So first, I want this new variety to have to be again smooth along its real locus. I also want its real locus to be close to the real locus of W, so that I have not changed real loci that much, and it will not mess up with my approximation problem. So I want the real locus of W prime close to the real locus of W. And again, as you asked, I mean that there is a diffeomorphism between the two, such that the inclusions are close for the C-infinity topology. And what I hope to gain is the information that the projection map is now injective on the complex points of W prime. So I restricted to the complex points of W prime is injective. And if we can do that, we win, because this difficulty does not appear anymore, and I can just define Y to be the image of W prime by pi. Then set Y to be the image of W prime by pi. Now its real locus is smooth and close to N, so we win. Okay, now what I need to do is explain to you what I mean by moving. That was your question. How to move. And of course, I cannot move in a naive sense. Typically, I mean, there is no reason why this subvariety should move in a family that will give a W prime that works. So you need to find another way to move, and I'm going to use an idea by Hironaka. So use Hironaka's moving by linkage. Technique. So what does it mean? So I fix an ample line bundle on this ambient space. Okay, then I choose an integer big enough, E, and I take general sections so the correct quantity, and the correct quantity being big N plus C, general sections in PNR times X of this power of L vanishing on W. Okay. So I have chosen the number of sections such that when I look at their zero locus of all these sections, well, it has the same dimension as W. And since I've chosen them of the same dimension as W, since I've chosen them vanishing on W, this zero locus, well, it contains W, and it contains also other irreducible components, like a residual variety that I will call W1. And in this situation, I will write W is linked to W1. So I use this symbol for to be linked. And really, this process of constructing W1 in this way out of W is called linkage. And the basic idea is that it is a way to move W. I can replace W by this W1, and it's a way to move it inside this big space Pn times X.
You assume W1 is the same dimension.
Yes, because it holds true because the sections are generic and I've not written it.
Sure.
Thank you. And so, okay, this is a strategy, but of course it doesn't work at all. Because this W1, well, to start with, it's very singular in general. So it's going to be singular even along its real locus. And in addition, I mean, it has no reason to be close to W. It's a different variety. W1 of R, the real locus, has nothing to do with the real locus of W. So I mean, it doesn't solve my problem. And so in Hironaka's paper, so of course he was not doing real algebraic geometry, so he didn't care about real loci, and he was looking at low-dimensional subvarieties. And when your subvariety W has dimension at most 3, no singularities appear. So Hironaka didn't care about these two problems. It was not important to him. But for our purposes, we need to control singularities and real loci. And so how am I going to solve these difficulties? So I'm going to, the idea is to apply linkage once again. So I mean, there is a way to reverse this link. So let me write it. I'm going to choose another very big integer. Let me call it f. And I'm going to take a section, another equation. Now I will require that it does not vanish on the real points. And I will choose it general. Non-zero, non-vanishing on the real point.
But before the FIs were real, right?
Yes, and this one is real. Its zero locus has no real points. Yes. And and finding sections for appropriate f with whose zero locus has no real points is not difficult. It's been explained in the talk by Michele. And now what do? I'm going to look at linkage with respect to these equations. Okay, it's not the good thing to do, but I start with this. Of course, f1 to fn plus c, they vanish on w1. So inside this zero locus, I have w1. And I also have a residual variety, which I'm going to call w2. And this shows that w1 and w2 are linked. And I'm not going to call it W2 because it's not the correct thing to do. I'm going to call it W2 question mark, just because it's not the correct thing to do.
Still, W is also...
Absolutely, that's why it's not the correct thing to do. But the point of doing this is indeed, since the only difference between these two links is the equation f, which has nothing to do with the real points because it does not vanish on real points, in the neighborhood of the real locus, these two links are like the same. they do the same. So W2 and W, they coincide in the neighborhood of their real locus. So in fact, W is equal to W2 along their real loci. So the good news is that now the real locus of W2 is smooth along its real locus, and its real locus is very close to the real locus of W. Well, of course, they're the same. But the bad news is that we've not really moved it. We were back to the beginning. So,
It looks like you are trying to show that along the real path, anything is a regular complete intersection.
sorry?
It looks like you're trying to show that along the real path, anything is a regular complete intersection.
A real local. I don't think it's okay. We start with something that is smooth.
Yeah.
So eventually, I mean, after applying links, it's not going to be the case. What do you? I don't think it's. I don't think it's true for W1.
Okay.
Right.
Along the components of it.
Yes. In my process, I will arrange that my varieties are always smooth along the real part, so it will be the case.
And given by the right number of equations.
Yes. Locally, yes. But of course, along complex points, there may not be a local complete intersection, and that's a difficulty in the proof, yes. Linkage does not preserve the property of being locally a complete intersection. Absolutely. Okay, so we solved the problem, but now what is bad is, but we've not moved. Okay, and so I'm just going to do a little variant of this construction. I'm going to additionally choose G1, Gn plus C sections of L to the E plus F, and epsilon a very small real number. And I'm going to consider linkage. Okay, so they're general and vanishing on W1. And I'm going to consider linkage with respect to the following equations. So I just perturb this construction a little bit. So the zero locus of these equations contains W1. There is a residual variety, which now I call W2. So W1 is linked to W2. And since this construction here is a small perturbation of the construction here, W2 is indeed very close to W2 question mark. So it is again smooth along its real locus, and its real locus is very close to the real locus of W. So as W2 is a perturbation of W2 question mark, W2 is smooth along its real locus, and W2 of R is close to the real locus of W.
How do I know that this new thing is still reducible?
That it is still what?
Reducible.
Okay, it may not be, and I did not ask that it should be irreducible, but if you make the choices generic, it is by Bertini's theorem applied.
I mean, you want it to be reducible. You want to
Oh,
have double components.
yes, because I chose the correct number of equations. This variety has the same dimension as W1. W1 is a subvariety of it. So
But no, but
W2 may be empty.
why the only one is a variety? You prefer it.
When I do linkage, I do not change the dimension of my varieties.
Okay, you have two lines, you perturb, you get conic.
Exactly. It-
So it becomes, I mean, you used to have two varieties, W and W1. Now
Yes.
it's one variety. So you're gonna.
Yeah, I do not care if my varieties are irreducible or not. All I care is that they have the correct dimension.
Like you want to single out W. Oh well, move W.
Yes.
So it's supposed to be conforming. Algebraically.
So let's look at the first link. W is irreducible of some dimension.
Yeah.
Then W1 is going to have the same dimension as W. And in fact, if you apply Bertini theorem, it's also going to be irreducible. You can verify.
No, we don't care about. Okay, so now you have two irreducible things.
Yes.
So the union is reducible. Now the union is perturbed somehow, right?
Yes.
So it stops being, and it stops being reducible. So you no longer have a component, well, which is close to W.
I don't know. All I do is apply such links. And if I apply them generically, I preserve irreducibility by Bertini's theorem.
G vanishes on W1. G's vanish on W1.
Yes.
G vanishes in W. Okay, sorry.
Yes, yes. To have W1 in it.
Okay, sorry.
I'm sorry. I didn't understand your question. Thank you. Okay. And let me finish very quickly. Okay, so this combination of two links, I call, okay, let me call it a pair of links. And it is the tool I use to move W inside this ambient space without perturbing its real locus too much. And my claim is if you apply sufficiently many, and in fact you need quite a lot. I need exponentially in the dimension pair of links. Pairs of links. Eventually you get a W prime that has exactly the properties that you want. You are able to move W enough to put it in general position such that 3 is satisfied. Okay, and that will be all. Thank you.